Okay, good morning to everyone. Let's start today's session. Okay, let's start today's session. And okay, so story so far with us is that what we have been going through is we have processes, we have events, we have interactions, and they generate data, and that data exhibits different characteristics, and statistics helps us in understanding those characteristics of different data. And then to understand our data better, we map our data to a given standard probability distribution. Previously, in the last session, we have seen what a probability distribution is all about. And we can have we can plot our data in terms of frequency distribution, or we can plot our data in terms of a probability distribution, right? Now, as we have seen previously that there are different standard probability distributions with us. Now, today we will go with each one, and we will try to get a non-mathematical understanding of each one, right? We will not go into any formula or any calculations. Rather, we will try to understand what different distributions are all about, and then we can map those distributions to our own problems, which we are going to tackle in future. So just by mapping our own problem or own process with this distribution is enough for us, because once you are sure about what kind of probability distributions, what kind of process you have at hand, and you map it with the probability distribution, then you can take along and dive further and further into that probability distribution, right? Now, many distributions follow a defined pattern of frequencies, and such pattern can be well described using some mathematical equations, and we will look into those a bit. So let's see the list which we previously saw, that we have uniform distribution. These are some standard distributions which we use most of the times, and they help us in different aspects. And the most important aspect of learning these distributions, and rather I should say the motivation behind learning these distributions, is that once you move into inference part of statistics, where you want to make forecasts based on some sample, these distributions are going to help you, right? So let's see how we are going to take on, and our task is to relate our data or pattern to any of the given standard distribution, right? And I have seen you, these are the standard distributions we have with us in our previous diagram. And then why we need to learn distributions: you are going to make inferences about this population based on the sample. You have a sample and you are making inferences based on that sample, right? Now, distribution is going to help you there. You need to be sure about what you are to infer, right? Well, what kind of things you are going to tell about the whole population based on the sample. You need to be sure about that. Here again, the distributions are going to help you, right? So actually why distributions are going to help you is that once you understand the process, once you understand the behavior of the data or the probability behavior of the data, then you can then you can be sure about what kind of outcome we have at hand, and we can just calculate the probability associated with that outcome, and based on the probability we can see, we can build a sort of a confidence about what we are going to infer from a sample. Right, now we will straight away start with the first distribution, the simplest one of all. This is called, you may have heard more about uniform distribution, right? So what is uniform distribution? If you have a process, I have kept it very simple. If you have a process and and that process has multiple outcomes, right? Let's say it has a 10 outcomes, right? And if each of the outcome has equal probability of occurrence, right? If each of that outcome has equal probability of occurrence, then we say this kind of distribution is a uniform distribution. Let's take an example. If I give an example of a uniform distribution, the simplest example is a coin, right? You toss a coin, either it lands as a head or as a tail. Now, if we are using a fair coin, then the probability of a head and probability of tail is equal, right? So it's 1 by 0.5 and 0.5 for each. So we can say the probability of these outcomes is equal. So we call this kind of distribution a uniform distribution, right? Now take another example. If you have a scenario where you have 10 different outputs, right? A process generates 10 different outputs, and the probability of each output is equal, then you can say we have the probability of each outcome is 1 by 10, right? So we have taken a generalized view. If we have n possible outcomes and each outcome has a probability of 1 by n, right? The outcome will be in a range of lower value and an upper value, and probability outside this range is going to be 0. Let's understand this with a diagram. Now you can look at this. You have, for example, this is a uniform distribution at hand. For example, you have outcomes between the range of A. It's very important to understand here. You have outcomes between the range of A, right? This is A, and you have up to the range of B, right? Okay. For example, you generate some outcome, and the value of that outcome, let's say you are generating a numbers, right? You are generating, a process is generating numbers, right? So you have numbers between 1 and 10. You can generate numbers between 1 and 10, right? So we have number, this is 1 and this is 10. So we can have number 2, we can have number 3, 4, 5, 6, right? 7, 8, 9, and 10, right? Okay. Now you can see probability of each outcome is same. So this is representing probability, right? So the probability of this outcome, probability of this outcome, or this outcome, or any of the outcome is same, right? So it does not change. So this kind of distribution is called as uniform distribution. Rather, if I draw it here, the data will always look like this, right? If this is the probability, right? So the data will be a straight line parallel to the x-axis, right? Then why we use this and where we use this uniform distribution is when you know your process is uniform in nature. Process uniform means that the process is generating outcomes at equal probabilities. Then you can calculate the values, or you can calculate the probability between any 2 points. For example, you have a range of 1 to 10. Now, if someone wants to know what's the probability that probability of getting a value between 2, sorry, this was 3, between 3 and let's say 5, right? Now, if you want to calculate this much of probability, right, you can use this formula. We have different formulas to calculate that, but eventually this helps you in order to understand the probabilities between some ranges, right? If you have a lower range and upper range, then you can calculate using uniform distribution. Okay. Then the uniform was the simplest of the all distributions we at hand, and Now we will move to another concept. I'm just giving an overview of these things so that once you have your problems at your hand, then you can relate your problem with some sort of distributions. Right now, if you have your own problem at hand, and you know that the process which I am trying to model, or the process which I'm going to solve is has outcomes, and the outcomes all of those outcomes have equal probabilities, then you can use the uniform distribution, right? Then we want to move to the another concept that's called Bernoulli concept, or Bernoulli process, or Bernoulli trial. Now, what's a Bernoulli trial? A process that has only two possible outcomes, right? Like, again, an example of a coin, or it has only two possible outcomes, a head and a tail. Or we can take another example of a process, which is a Bernoulli process, is like either you fail in a test or you pass in a test. Now, this is again a Bernoulli process, right? So a process which has only two possible outcomes. So the maximum outcomes are two and one at a time, right? And each outcome has its own probability, right? It's not necessary. Now, see, in normal uniform distribution, you saw that each outcome has equal probability, right? Now, a Bernoulli process is a process which has only two possible outcomes, right? And each outcome has its own, not necessarily that outcome one has the same probability as outcome two, right? For example, we don't have a fair coin and we flip a coin. Then if the probability of head is 0.7, and thus the probability of tail will be 0.3, right? So we have head and tail. So this is a Bernoulli process. We have only two outcomes, and each outcome has its own probability. Sometimes you may ask that how about the probabilities being equal, right? Yes, we may have a Bernoulli process where the probability of outcome one is equal to probability of outcome two. So this is 0.5 and 0.5, right? Half probability with this, half probability with this. So that kind of process is called a Bernoulli. It's very important to understand the concept of Bernoulli process in order to understand the further. We have one or two or three distributions to understand based on this concept, right? So Bernoulli process, again, it's a process where we have only two outputs. Any process in the world which has only two outputs is called a Bernoulli process. And also, the outcome one and outcome two, they have their own probability. Not necessarily they have equal probabilities. Now, I have just given this this equation here, or relationship here, which you see in the most of the literature. You see this. If you see something like this, so this means that this is a variable, and we call it a random variable, which takes two values. Actually, one represents the outcome one, and zero represents the outcome zero, or vice versa, right? So don't worry about one and zero here. Okay, so this is the outcome one. It has a probability of p, right? And outcome zero has a probability of 1 minus p. And you know that when we combine the probability of 1 and 2, it should come up 1, right? So this is a Bernoulli process, right? Once you understand the Bernoulli process, then we have a Bernoulli distribution. Now, what's a Bernoulli distribution? Simple. A Bernoulli distribution is a distribution where we have only two possible outcomes, and each outcome has its own probability. For example, this is 0 and this is 1. This is outcome 1. You may call it 1 or 2. This is outcome 2, no problem. We represent by 0 and 1. Now you can see the probability of this 0 is 1 minus p. So the outcome 1 has a probability of 1 minus p, and the probability of outcome 2 has p, right? So this is a kind of a Bernoulli distribution, right? Now, another distribution based on Bernoulli is called geometric distribution. Now, just keep a track of what we are doing. We have understood Bernoulli process. Bernoulli is a process where two outputs, maximum two outcomes possible, and each having its own probability. Now, we have another kind of Bernoulli distribution, That's called geometric distribution, which you may have heard about. What it is, I've kept it very simple. You're repeating a process that has only two possible outcomes. Means you're repeating a Bernoulli process. Now you're flipping a coin once. This is a Bernoulli process, right? Now, if you're flipping a coin many times, right? You're repeating your coin flip until you get the first outcome of your interest, right? I have added this term outcome of your interest. Why? For example, you're looking for a head and you're flipping the coin until you get a head, right? Right. So that kind of distribution is called geometric distribution, right? So you're repeating, flipping a coin, you were looking for a head, you're flipping a coin, you got a tail, you're flipping again, you got a tail, you flipping again, you got a tail, you flipping again, you got a tail, and you continue this process, you continue this Bernoulli process until you get a outcome of your interest. Let's say you were looking for a head. Now, in most of literature, you'll find this outcome of interest as success. We call it success, and the another outcome we call it failure, right? Now, for example, take another example of a geometric distribution is that you always want to pass a test. Now you go through the process and you got to fail. You again go to the process. You got to fail. So you keep on repeating this process of testing yourself until you get a success, until you get an outcome of your interest, right? Your outcome of interest always to pass a test. So that's called a geometric distribution, right? Now, this is how a geometric distribution looks like. And you can see now at first, it has a probability of 0.2. Why it has a probability of 0.2? Let's understand a bit. Now, for example, your outcome of, so we have a Bernoulli process and each outcome has its own probability, right? For example, the process 1 has has a probability of 0.7. Sorry, outcome 1 has a probability of 0.7 and outcome 2 has a probability of 1 minus, that is 0.3, right? So they both add up to 1. If outcome 1 has this, now if the outcome of your own interest, if you're looking for this one, so it has a probability of 0.7 at the start, right? And the failure has a probability of 0.3, right? So you can look here now. This is a geometric distribution, and your outcome of interest has a probability of 1 by 5. 1 by 5 is 0.2. That's why you can see this is 0.2 at the start, right? Then you keep on repeating this. See, you keep on repeating. He performed this Bernoulli once, again, right? You are keep repeating this until you get a success, right? Until you get your success. That's why we call it geometric distribution. And the curve will always look like this. Right? So this is a geometric distribution. We are repeatedly performing a Bernoulli process. Now, one more important aspect with these is that each of your process should be independent of the previous one, right? So each of the trial or each of your repetition or iteration should be independent of the previous iteration. Okay. Then another kind of Bernoulli distribution, we call it binomial distribution. Now, previously, you were repeating until you get a success. Now you are performing this Bernoulli process n times, and you're looking, and after performing n times, you want to find how many times I got the success. Let's say you're 10 times flipping a coin, and you were looking for a head. Then once you complete 10 flips, then you're counting how many flips I got. Okay, I got 7 flips out of the 10. So you are repeating a Bernoulli process n times, and then you are looking how many times my interest or my desired output came, right? And that's called a binomial distribution, right? So binomial distribution is nothing. It is performing or repeating your Bernoulli process n times, right? Don't get confused with this geometric distribution. Geometric distribution also performs it n times, but the n stops where you get the first success, right? Here you stop where you get the first success, and here you don't stop. You have decided that I will perform this process n times, and then I'm looking for success. Now, if n is equal to 1, if you're just repeating the Bernoulli process once, and that's what we call a Bernoulli distribution itself, right? So if n is equal to 1, this is a Bernoulli distribution, right? So now let me give another example before we move further, is that if you are appearing in an examination and you have 10 10 questions, and each question is an answer of a true or false, right? Now if you are now see 10 questions and each question is an answer of true or false, right? Now performing one question means you are performing a Bernoulli process, right? You're performing Bernoulli process. Now if you're repeating it 10 times, right? This is a binomial distribution, right? You're performing it 10 times, and then how many you got right, right? How many of them you got the right is the outcome of a binomial distribution, right? Now, if you are performing this test in a way that you will stop where you get the first right, right? You answered the first question, it got wrong. You answered the second, it got wrong. You answered the third, and it got right. Now, this kind of distribution is a geometric distribution, right? So you can understand the scenario. Same single question paper, 10 questions. Each question has an answer of true or false. So one question depicts or represents a Bernoulli process. You're repeating it 10 times, then it's a binomial distribution, and you can have 7 or 8 corrects. Now, if you're repeating, if you're performing those questions or if answering those questions until you get the first question answer right, and you are stopping there, then it is an example of geometric distribution. Okay. I hope this is clear. I'm not going into the mathematics of these distributions, because you must relate your own problems with it. Once you relate the formula, using the formula, and everything is easy in Excel and in literature as well. Okay, then let's move to the next process. We have finished with the Bernoulli process, and you have seen the Bernoulli process as Bernoulli distribution. It is a binomial distribution, and it also has a geometric distribution. Okay, and we also have some negative binomial distribution and others. They are just variants of those Bernoulli processes, right? Now another process which is called a Poisson process, and this is a very important process. A process which generates a particular outcome. So this is process is not going to generate two outcomes just like we were doing in a Bernoulli process. Here we can have so many outcomes, right? A process which generates, and we are concerned about a single outcome out of so many a process may generate. A process which generates a particular outcome where we know the average time between two consecutive outcomes, right? We know the average time between two consecutive outcomes, but we don't know the exact time of the outcome in a Poisson process. Now, a process generating outcomes. For example, you're driving a car for 100 kilometers, right? Now you may encounter another car crossing you in an opposite direction. Then but if you know the average time between two cars encountering you or crossing you in an opposite direction, but you don't know exactly at what time the car will cross you, that's called a Poisson process, right? I hope this is clear. This is called a Poisson process. And the Poisson process is mostly applied in concepts where you have to evaluate something with respect to rate, right? With respect to time, or with respect to space or distance or something. So it's all about rate of occurrence, right? Rate of occurrence of something. And when you have a process where you want to calculate the rate of occurrence of something, or you want to guess when the next thing is going to happen, you use Poisson process. And some of them call it Poisson, and we call it Poisson, right? Okay. Now, what are the properties of Poisson process? The number of occurrences of the outcomes of interest can be counted. The first property. Okay, let's go to an example and then we will understand. Let's take an example of Poisson process. One example of a Poisson process is the number of births per hour at a given hospital, right? You have a hospital and you have number of births per hour, right? For example, uh, suppose a particular hospital experiences average of 4 births per hour. Now, see, there are 3 things and I have just colored them. Now, you know the average. So average is 4 births and unit time. In 1 unit time, this is the unit time. So, 4 births per hour in a hospital in a given unit time, right? So let's move back. This kind of process is a Poisson process, right? Okay. But you don't know exactly at what time the next birth is going to happen, or you don't know exactly at what time the birth happened, or you cannot calculate it before, right? So you don't know it rather before, but you can calculate it using Poisson. Now, these are the properties of a Poisson process. The number of occurrences of the outcome of interest can be counted. You can count how many births happened in 1 hour, right? Right, you can count it in a hospital, how many births happened in. You randomly entered into a hospital and then you started calculating how many births happened in 1 hour. Like say you got an answer of 10 births in 1 hour, but your average was 4, right? Right? Your average was 4. And the mean number of occurrences of the outcome of interest during a specific interval of time is known. You know the average, right? You know the average, it was 4. And one more property and one more other very important thing is that each outcome is independent. The probability that an outcome of interest here in terms of a hospital birth is a birth, right? Birth of a baby will occur is proportional to the size of the interval. What does it mean? It means that if you increase the size of the interval, if you're looking for 1 hour, and if you increase it to the next 2 hours, if you, as you're increasing the interval, the probability that more births will happen will increase, right? This is a very common sense, right? Now, this is a Poisson process. Again, keep in mind that you have a hospital and you went into a hospital, you calculated the number of births, right? And those all births, calculated the number of births, and the average number of births at the hospital was 4, but you got 10, right? Then you can say that this kind of process is a Poisson process. Now, where we use mostly this Poisson process, you use this Poisson process when you have, okay, you use this Poisson process, like if you want to calculate the number of accidents, right? Or road accidents, kind of road accidents. Now, you know that average road accidents for these 50 kilometers is 2 accidents per 2 days, let's say, or per 1 day, or per 24 hours. Any unit you can use. Let's say per hour, 1 accident per hour for these 50 kilometers. Then you want to forecast when the next, when the next accident is going to help. And if you want to forecast kind of things, then you may use what we say Poisson distribution. Okay. Now, like this. Okay. So here we go. Now, Poisson distribution. Based on a Poisson process, we can have a Poisson distribution. Actually, based on Poisson process, we can have 2 distributions mostly which we use. One is called, one of them, the first one is the Poisson distribution. The Poisson distribution describes the probability of obtaining n outcomes of interest during a given interval. Now, you want to see the probability that, what's the probability that 10 births will occur in a given hospital, where the average, you're given the average of 4 births, per hour. Now you want to see the probability that, what's the probability that 10 births will occur, right? Or what's You are given that during these 50 kilometers, you have 2 accidents per hour. Now we want to see what's the probability that 10 accidents per hour will happen. Only average is given to you, right? And you want to calculate the probability of it. Then you use Poisson distribution. It's the simplest form of distribution. Now, Poisson distribution, you relate in terms of distance, what we call space, or you relate it in terms of time. Most of the time, rather, we use Poisson distribution to calculate the probability of some event outcome, probability of an outcome rather in a given unit of time. Okay. Then let's move further. This is a formula. I don't really want it to be using any kind of formula here, just to give you a glimpse of once you use a Poisson distribution. You know, you have so many statistical tools which can get it done for you, but just I wanted to give some importance to this lambda, right? Whenever you see a Poisson distribution, something like this, and you see a lambda here. Now, what's the lambda? Actually, in a Poisson distribution or a Poisson process, the only thing you know is the average number of outcomes you know beforehand. So this lambda is always available to you. Like in the previous example, I told you that we have average 4 births per hour in a hospital, right? So that's the lambda. Lambda is the average, right? Which you have. And K is nothing. K is that, how many number of, outcomes of interest which you are expecting. Let's say you were expecting 15 births per hour, right? Then if you want to calculate the probability that 15 births per hour, so K here is 15, and you want to calculate the 15 births per hour, you can use this formula, this simple lambda, this is the average, and you raise it forward by K, and then you multiply it by E, that's Euler number, and then you power it by minus of the average, right? And then you whole divided by K factorial. So no need to go into the details on this. Just you should know that whenever you have Poisson form distribution, you should always be given this lambda. That's average should be given to you, right? This is E, and this is a Euler number, and I don't want to go into detail what this Euler number is. It's a constant, and this value is 2.71. Something, right? And some of you may be interested in E. It's a very interesting concept, and I would suggest that all of you go through what E is. It tells you something about the growth, right? It tells you something about the growth of. So you should learn what E is. But here we don't need it. Just use it and make your life easy, right? So this is the Poisson formula. Okay, then. What kind of shape this Poisson distribution it has, it purely depends on the lambda. Now, the lambda is the average, right? Now, if you have a low value of lambda, the distribution will look like this. See, the distribution will look like this. And if you have a median lambda or a medium size of lambda, the distribution looks like this. And if you have high lambda, it goes normal distribution, right? It's just like a bell curve. Now, why this happens like this, and once you go through in deep, if you want, you can. If you don't want, it's not necessary for you to solve your problems. Just make sure that the lambda you have is correct, and so this is the most important part of your calculations. So focus on your lambda. So this kind of shape you may have. Then one more distribution related to Poisson that's called exponential distribution. Before we take a break, let's finish this. The exponential distribution is the probability distribution that is used to model the time we must wait until a certain event occurs. Now, this is all related to Poisson distribution. Poisson distribution tells you that, okay, one event happened, second event happened, right? And you know the average of events, then you can calculate how many events going to happen in a given unit time. And Exponential distribution tells you that what's the time between the event which happened now and the next event, right? It gives you a time interval between any two Poisson outcomes. Now, this is very important. Where does this distribution help you? I mean, say the exponential distribution. Just read them out. Just read them out. Hello? Okay. Just read them out and where we use. If you want to know how long does a shop owner need to wait until a customer enters the shop, you can use exponential distribution because it tells you the probability that when the next event is going to happen. If a customer enters now, what's the probability that what's the time, right? What's the time that the next what's the time between the first customer and the second customer? You can calculate it using exponential distribution. How long will a laptop continue to work before it breaks down? Yes. So in terms of reliability analysis and other things, you use Poisson, you use exponential kind of distributions, right? And how long will a car battery? The same. Now, how long do we need to wait until the next volcanic eruption in a certain region? Now, you know, a volcanic eruption happened today. Now, what's the probability and how long it's going to take another eruption to come up, right? So these kind of answers, or if you're looking for these kind of solutions, then it's always the exponential distribution. Rather, the Poisson process itself is important to understand, right? So let's take a break and we will join after 2 minutes as we do.